Okay, so this is lecture 2, part A of the liver. This is going to be a multi-part lecture that's going to cover both diffuse processes, including a brief review of some relevant MR physics, followed by a discussion of more focal processes. So just like in the pancreas module, multiple choice questions for radiology tend to fall in these 3 basic categories. So let's start with a sequence question. What is the T1 relationship between the liver and the spleen? In other words, which one is brighter? This is something that a lot of people sort of take this knowledge for granted. It's in your subconscious somewhere. Like when you look at an MR of the abdomen, if it's abnormal, it just sort of looks abnormal. But without a picture, this kind of question can be confusing, which is why I bring it up. So on T1, normally the liver is brighter than the spleen. And the way that I remember this is that the pancreas is full of enzymes. It's T1 bright. The liver is also full of enzymes. Therefore, it's T1 brighter relative to the spleen. Pancreas is still the brightest. Which brings us to the opposite question. What about on T2? There's 2 ways to remember this. One is the other one is the other one, meaning that the spleen is brighter and the liver is darker. Or you can just remember that the spleen is sort of a big bag of water, and that one of its main jobs is to collect blood. So you'd think that it would be a sack of water. All right, so let's look at the next case. All right, so we've got a axial CT. Looks like it does have contrast on board here. We'll zoom up. All right, so let's try to orient ourselves here. Obviously, we're zoomed in on the liver. You know this is a liver case because it's a liver module, but let's pretend that you don't know it's a liver module. You're seeing a lesion here, hypodense, but I want to point out something else also, because as a modern radiologist, you look at things in 3 planes, and you scroll up and down to sort of orient yourself, but you don't have that luxury here, so I want to point this out to you here. Right there. Notice those clips, okay? So when you see those clips, you're right at the gallbladder fossa. So immediately you should be thinking to yourself, what happens right near the gallbladder fossa? So you're also nicely provided with some MRI sequences, and anytime you're given in and out of phase imaging, you need to be thinking about a fat case, right? So in and out of phase, it's going to be a fat case. It's going to be an adenoma case. It's going to be a focal fat case or a focal fatty sparing case, and obviously that's what this is going to be. So remember, they've only got so much real estate on the screen, and they're only going to show you, they may show you a bunch of different sequences to try to confuse you, but if in and out of phase is provided, you for sure have to look at that specifically with a bias that this could be a case that has to do with fat. All right, so here we can see we've got in phase and out of phase. Out of phase, the out is the outline. That's how I remember that, outline on the out of phase. And we're seeing signal dropout. So you can have focal fat or focal fatty sparing at the level of the gallbladder fossa. The key trick is to look when they're giving you in and out of phase imaging to be immediately biased. Boom, this is probably a fat case. All right, and they're classic locations for focal fatty infiltration. Which is this case, but you can also have focal fatty sparing, which would be the opposite on the in and out of phase dropout. So be ready for the physics follow-up questions, and now's as good a time as any to integrate that right into this talk. So let's review that real quick. So with fat, there's two main types of artifacts. You've got your type 1 chemical shift, and then you've got the type 2 India ink or dark line artifact. As you may remember, part of MRI is localizing the signal to a particular voxel or point in space. And this is done with the application of a gradient, frequency encoding. So a gradient is placed, and that lets you say that something is at one spot versus another spot. This is I'm not a big formula person because I don't think that formulas are helpful for this particular exam, but this is one particular formula that I think is helpful and worth remembering. This particular relationship. So frequency equals the field strength. That's the strength of the magnet, 1.5 or 3 Tesla, times the letter Y, which is this constant, the gyromagnetic ratio constant. It's irrelevant. It's just a constant. So fat and water, they're different. This is the key point, is that they're different. They spin different. Water spins fast. It's inefficient at T1 relaxation. In other words, it is a long T1. Fat spins slowly and is efficient at T1, has a short T1. And the reasons are complex. Electronegative oxygen atom pulling protective electron clouds away from the hydrogen nucleus. All that's irrelevant. What matters is that you just recognize that these things are different. And because they're different, they're going to have slightly different frequencies. And that is going to cause a problem when you try to localize them. So this is an example of this type 1 artifact where you have a little bit of a white line crescent on one side and a little bit of a black crescent on the other, where things just aren't localizing quite perfect. So let's go back to this. Let me point out something that's very important here. Notice that we got white here, black, black, white, black, white, black, white, black. It's occurring in this direction. This is the frequency encoding direction. Remember, that's frequency, and this is the phase encoding direction, and this is the one where you get your pulsation artifact. Now, who cares? People who write test questions care, and that's the only thing you need to know. The follow-up is, how do I know that's frequency and how do I know that's the phase encoding? Well, by convention in body imaging, it is, because the phase encoding direction is supposedly the shorter one for time thing, and frequency is the longer one, where you're having more space through, and it all has to do with table time. Now, what's the exception? Remember, exceptions are testable. The exception is breast. If you're imaging the breast, they tend to flip it. The reason is you don't want stuff pulsating, either from respiration or from the aorta or the heart, which is right behind the breast, into the field of view so that you can't tell what's going on. Because you really need to be able to overcall stuff and perform unnecessary biopsies. So you want to be able to really see those things that you're going to perform unnecessary biopsies on well when you do breast MR. So so they flip it. So this would be phase encoding direction and breast. But for abdominal imaging, phase encoding, just remember that picture of the aorta with the pulsation artifact, and frequency encoding in this direction. Remember this picture where it's white, black, in that direction. All right, so this is another way that MR physics they love to ask questions about what makes it better, what makes it worse. If we remember our formula, remember we had differences in frequency, and that equaled field strength times a constant. More field strength, or a more powerful magnet, a 3 Tesla relative to a 1.5, is going to make those differences more noticeable. In other words, a higher field strength makes the artifact worse. So what about receiver bandwidth or readout? I'm a visual learner. I try to make things visual when I have trouble remembering them. You may be easier just to remember this concept, but this is an attempt to make it a visual concept. So I've got a red line here that is going to be our fat or high bandwidth, and this is our low or our narrow. If we look at a frequency change that's pretty small, pretty narrow, like that, it's going to make sort of 1 pixel difference, a 2 to a 3. And this is on low. Now if we make a fat one, like this, that's going to make the same difference also. So in other words, differences in frequency are less noticeable when we're dealing with a high bandwidth here. This is a readout. So if we moved a little bit, we got a big change. If we moved a lot, we got the same change as long as we were dealing with the high. Or you can just remember, less noticeable at high. Alright, so that is type 1. Now let's talk about type 2, which is the one most people are more familiar with, this in and out of phase, or India ink, or dark line. So remember we said that water and fat operate differently, and they move at different speeds. The analogy that most people will use when they teach this is 2 runners on a track, a fat one and a skinny one. The skinny one is going to run faster, and he gets ahead, continues to get ahead, and at one point he is going to be directly opposed to the opposite runner, the fat. And when this happens, you have cancellation of signal. And then they continue to run, and then he's lapped him, then they overlap in phase. And then you get this kind of picture. And then they continue running, and then they're opposed again. And this would repeat forever, right? So they're going to be opposed and then in, and then opposed and then in, and opposed and then in, and opposed and then in. He'll continue to lap him on the course over and over and over and over and over again. And that happens about every 2 seconds. So this is a continuing phenomenon. So let's review, and in my opinion, this is the most likely way that this kind of stuff gets tested. Now, why is it tested like this? Because the people who are writing the questions actually don't know any physics. Do you know how much physics they know? They know exactly as much physics as you do once you finish this test. Because what are their qualifications to write these questions? They passed the old written physics test, right? Remember that one? The one that had like all the questions recalled? There's probably a book somewhere in your resident library that is the old Huda book that somebody has like in the margins written what all the questions were. So they passed that test, and that makes them an expert in physics to write physics questions for you. These people aren't actually physicists. They are radiologists in academic specialties, breast imagers, body imagers, MSK imagers, who were asked by somebody to write physics questions or volunteered themselves. They opened up Bushberg or Huda or whatever textbook they were going to use, read the paragraph on fat artifacts, and then wrote questions based off of that. See, I can almost guarantee you that's how it went down. And because of that, you can predict what those questions are going to be. They're going to be basic. They're not going to be super complicated like in-depth physics. I remember that when I was trying to learn physics, MRI physics, for the first time, that I was super duper stressed out because I was like, oh my God, this is a bottomless fucking pit. It just goes on and on and on. How am I supposed to know all this shit? There is like volumes and volumes and volumes. It's like, well, you don't need to. And that's the point that I'm making. You don't need to. You can get away with superficial knowledge compared to the Japanese rock star who is singing the 80s song in English in Japan, but can't even speak English. He doesn't know what the words mean. That you can actually get away with that. You can just be reciting facts that you don't even understand them because the person who wrote the question doesn't understand them either. So don't panic. So let's take a look at these. Type 1 artifact. Remember, that was the artifact that has to do with the gradient being placed and the differences between fat and water causing localization problems. And I made a huge deal about it only occurring in the frequency encoding direction. Now, it becomes worse with, remember that formula, high field strength, so 3 is worse than a 1.5, and is more noticeable at a narrow receiver readout bandwidth. It occurs with both spin echo and gradient. That's not relevant. Type 2 are dark line or India ink. The dropout occurs on opposed phase, and it only occurs with gradient echo. And if you remember that, by definition, a spin echo sequence has a 180 degree refocusing pulse, imagine that would just be resetting that race over and over and over again. Like a referee that's blowing the whistle every 5 seconds. I'll get back to the starting line. So if you have that happening over and over and over again, the Kenyan cannot get ahead of the fat guy. You know, the skinny guy can't get ahead of the fat guy on the race to where you can have them to be opposed or lined up with each other. So this is the classic follow-up question. We've got in and out of phase with patient A, and an in and out of phase with patient B. And we notice that with patient A, the top one, signal is dropping out on opposed phase, and we just said that is fat. The bottom one is the opposite. It looks like that the signal is actually dropping out on in phase. And that, you may know, is hemochromatosis. And we're going to sort of talk about why now, because I think that makes for some good multiple choice questions potentially. So in theory, the magnet creates a homogeneous field, but that's just theoretical. That's not actually what happens. In reality, it's inhomogeneous. So there's this thing called T2, which you've probably heard of, but there's this also a thing called T2 star, which is like T2 plus all the inhomogeneities in the magnetic field, the ones that are from intrinsic defects in the magnet itself, or susceptibility-induced field distortions from tissue or materials within the field. So things that would make this worse would be metal, air, think about anything that blooms is like a magnet inside of a magnet. And that's causing the field to become distorted or inhomogeneous. That's your T2 star, okay? And that gets worse over time. It becomes more noticeable. So let's sort of contrast the fat dropout signal versus the signal dropout that occurs with T2 star effects. So we said that the signal drops out with fat and water as the runners become like 180 degrees apart from each other on the track. That's why it drops out. And that's a thing that repeats. Every 2 seconds they're in, or they're out, they're in, they're out, they're in, they're out, they're in, they're out, they're in. So if we kept going 8 seconds, 10 seconds, 12 seconds, you would see this continue to repeat. Whereas a T2 star decay gets progressively worse as time goes. All right, so now I've added the MR pictures here, and this is fat. Okay, this is fat. So opposed, it's out, in. You see the signal return. Opposed, it's out again, and the next one would be in, right? But what if we look at what would happen with the iron in the liver from the T2 star? That's the bottom row. Notice that as time progresses, that it gets progressively darker. More and more and more and more and more T2 star effect. So this is what we're used to seeing. The opposed phase is obtained at 2 seconds. For fat, it demonstrates the signal dropout as the fat and the water are directly opposed from each other. And then on in phase, which is acquired at 4 seconds, they're lined up. You see the signal return. And then for your iron-laden liver, at the beginning, T2 star is not real noticeable, and then at 4 seconds, it gets progressively worse, so you have a darker liver. And these are opposites, right? Dark on opposed, fat. Dark on in phase is hemochromatosis, and you probably memorized that. But let's take a look at some fuckery here. All right, what if we waited? The tech was asleep. He's playing on Facebook, and he didn't bother to image at 2 seconds. Instead, waited at 4 and was just like, it's okay, that opposed phase will come again at 6 seconds. I'll just pick it up then. Now we have signal loss on the opposed phase, which we'd expect with fat, but also our iron-laden liver looks darker on opposed relative to in phase. So you can't tell the difference between these. So this is both have lost signal on the opposed phase, right? So does it matter if you do the opposed phase first, the 2 second one, or can you just wait? It totally matters. You have to do the opposed phase first. You have to do that. You have to scan them at 2 seconds and 4 seconds. Otherwise, you can't tell the difference between an iron-laden liver and a fatty liver. That is highly testable, and it's highly practical. And the way to remember it is time is money. Why would you ever skip the 2 second one? Don't do that. There's no reason to do that. And the way to remember that the opposed phase comes first is if you think about them on the track, that he's going to end up 180 degrees across from him before he makes it all the way back around to lap him. Let's look at some other ways that you can test this. So here's in phase and out of phase. Remember that the out of phase is obtained first by convention at 2 seconds, and the in phase is obtained second by convention at 4 seconds. Take a look at the air in the bow. Have you ever noticed that? Notice that it turns darker on the in phase? That's that T2 star effect. It's blooming progressively worse over time, and that would become even darker at 6 seconds if you obtained it then. You can do the same thing with clips. You could write a question that was something like, they show the blooming get progressively worse, and they sort of cone in on it to make sure that you couldn't see the dark line artifact, or mess with whatever, but just showing you that blooming is getting progressively worse, and like which of the following was obtained first. Blooming gets worse, so the less blooming is obtained first, the worse blooming is obtained second, because of that T2 star effect. Air anywhere, including in the liver, could be, you could do it like that too. So what are some other sequences that employ T2 star? The obvious one would be anything that's heme sensitive, right? Because we talked about blooming and a magnet inside of a magnet, and that creating an inhomogeneous field, and therefore making things darker quicker. The other one that a lot of people haven't thought of or don't think about is functional MRI. And the reason that functional MRI works is you're going to move your arm or whatever, and that part of your brain needs more oxygen. So it's going to pull in more oxygen, and then you're going to have more carbon dioxide, and then there's going to be like a washing in of blood. And so there's going to be all this physiology that's taking place. But the fundamental change or difference is the paramagnetic properties between oxygenated hemoglobin and deoxygenated hemoglobin. deoxygenated hemoglobin being paramagnetic, whereas oxygenated hemoglobin is not. And therefore, the former will cause local dephasing of protons and thus a return of signal from the tissues in the immediate vicinity. Whatever. Just there's a change in the oxygenated hemoglobin to the deoxygenated hemoglobin, and as far as its magnetic properties, and that is something that can be measured, and it takes advantage of that T2 star effect. All right, moving on. So we've got a patient here with a dark liver, dark spleen, dark vertebral body. The liver is darker than the paraspinal musculature, that's not normal. And then we look at patient B, and we see some pancreas here and here. Same thing here, pancreas, and the pancreas is losing signal here also, okay? So this is two different kinds of hemochromatosis. The primary kind that involves the pancreas, PP. The secondary kind that involves the spleen, SS. Primary hemochromatosis favors Caucasians, and it tends to affect women later in life relative to men, because women menstruate. Therefore, they sort of bleed that iron out. And it can create the step one question, which is this bronze diabetes, where you have a change in the skin color, and because your pancreas is fucked, you become diabetic. And then the secondary type, which occurs from frequent transfusions, and this is obviously much more common. As a general tip, the liver should never be darker than the paraspinal musculature, and if you see that, you should be thinking that that is AB normal. Here's an MSK correlate. If this was the hand of a hemochromatosis patient, where would you expect the disease to affect? And the answer would be MCPs and the TFCC. Remember, it's the hooked osteophytes that they get classically at this location. And the other entity that gets hooked osteophytes is CPPD in the same distribution. All right. Next question. All right, remember, what do we do first? What are you showing me here? It's a CT. What's the cut through? Cut through the liver. Is it contrasted or not? Well, it's not, right? Look at that. That's non-con. That makes this a very, very dense liver. Remember, this is a differential case, and when you see that. And it can be a few things. Iron, thorotrast, which almost certainly will make an appearance on the test of the future. Glycogen storage diseases can do that. But for the purpose of multiple choice, when you see dense liver, it's always amiodarone, right? It's always amiodarone. So dense liver, it's usually an incidental finding. You can have lung involvement also, which can be symptomatic. The lung involvement tends to be a chronic interstitial pneumonia pattern. Favors the lung base, is it peripheral? Sort of looks like that. And the way that I remember this is that the lung bases are close to the liver. It's going to be dense, sort of patchy crep. It just looks like that. All right, so this concludes part 2, and we'll continue on with focal disease in the liver.